Hello, my name is Sonika Kurode, and this is my Falling Slinky Lab for Physics 2211 in Dr. Curtis's class. So I used the video of the falling slinky to observe the motion of the bottom of the slinky. The first model is observational, which is using the video from YouTube to analyze in Tracker, and Tracker allows us to analyze the real-life scenario of the falling slinky. Model 2 is the predicted model, where I created a computational model of the falling slinky using data from Tracker. And we're going to compare the observed model to the computational model to analyze motion of the bottom of the slinky. So the fundamental physics principles in this are force of gravity, air resistance or drag, force of tension, which in this lab is going to oppose the gravitational force, and Newton's second law, where we use the derived update formulas to see the change in position and velocity over time. So using all these formulas, and we use all these formulas to input into the computational model. So a quick overview of the result is that we find out that the bottom of the slinky remains stationary as long as the tension force is equal and opposite to the gravitational force. So for the tracker model, the system is the slinky, the surroundings are the earth, which creates the drag and gravitational force. The initial conditions are the mass of the slinky is 0.218 kilograms, and I found this initial position using tracker, and the initial velocity was 0 since the slinky wasn't moving in the beginning. Here is the tracker analysis. I set the origin as the bottom of the slinky since that's the motion that we're trying to analyze. And then I just kept tracking the motion of the bottom of the slinky as the slinky was dropped from that height. Here is my code. So first, the drag force value I found using trial and error. Then in the first loop, t is less than 0.617, and this is the time from the top of the slinky being released until it met the bottom of the slinky. In this section, W is the gravity force, or mgh. Force of tension is equal to the opposite force of gravity, which I wrote there as Ft equals negative W. And then force net is equal to the gravity plus the force of tension. Then after that, I just updated the position and velocity, and that kept looping through until you reached the end of that time at 0.617. And from 0.617 to 0.750 is the time from the bottom of the slinky hitting the ground. So over here, W is still the force of gravity, but since there is no tension anymore, drag comes into play as the slinky falls, so I put the equation for drag there as Fd. This time, Fnet is equal to gravity and drag, and then again, I just updated the velocity and position through the loop. So here is the graph of the observed data versus the predicted data. You can see that the observed graph is more or less the same to the predicted, with the observed graph being slightly higher. The real-life model will always have some discrepancies since the computation model is the ideal scenario with elements that the user manually inputs. So some sources of error could be that since I was clicking the points on tracker, there could have been some human error there. And because I used trial and error to find B, that could also create some error in my drag force value. So why does the bottom of the slinky stay stationary? It stays stationary because force of tension is equal to force of gravity as the top of the slinky meets the bottom of the slinky. So, and then once they meet, tension disappears, or it reaches 0, and the gravity overcomes the new upward force of drag, which causes the slinky to fall down. What if there was a weight attached to the bottom of the slinky? If the weight is heavy enough for gravity to overcome the tension force upwards, then the bottom of the slinky would fall as well. But if the weight is not strong enough and gravity still equal tension, then the bottom of the slinky would still stay stationary until tension equals 0. Thank you so much for listening. I hope you have a great day. Bye.